All right, welcome to the, what is it, fourth review session. So yeah, we will have tell me your name again. Sorry. Michael will do the first problem. Okay, so maybe start off, by highlighting the parent chain in red. Can you? Yeah. Thank you. I'll take you like an apple. Let's see. Maybe we switch. Let's switch to a different color. Sorry, I'll get you the apple.
Don't forget a dash right
there. Okay. 3,6-dimethyl octane. Okay. Thank you.
He's got an orange for you.
You got an orange for me. Thank you so much. All right. Let's take a look. 3,6-dimethyl octane. Yeah, you put a dash in between, so I'll just write it once more. Right? So make sure you put the dash, right? And then the dimethyl octane. So that's great. Yeah, and this is actually fairly straightforward because it doesn't matter which way you count, right? If you start from the right side or from the bottom side, you get the same answer. Okay, so this is 1, 2, 3, 5, 6, 7, 8. Okay, any questions? Makes sense. So let's go to the next one. Who wants to try this one? Yeah, okay. Okay. Do you want an orange or an apple?
Apple?
Okay. Maybe start by highlighting the parent chain. Let's see. Yeah, you have to click. Sorry, you have to click on this one. Maybe let's pick the red here. Yeah. Perfect. So the parent chain here is the ring. Remember, that's you just pick the ring. You don't pick the stuff coming off of it. Okay. Here we go. Okay. All right. Do you guys have any questions? These are easy ones. Maybe I should have given you harder ones. Yes, please.
So when you're numbering a ring for like substituents, do you always start with like numbering like the alphabetically first in the alphabet first as 1? So
yeah, the question this is a very good question. If you're numbering a ring, do you always start with the one which starts first in the alphabet? And the answer is only if there is a tie.
Only if there's a tie.
Okay? The first rule of numbering will be based on so that the second substituent also gets the lowest possible number, right? Because the first substituent will always get number 1. But the second substituent also gets the lowest possible number. So for instance, something like this. Let's make up another example. If you had something like this, how would you number it? You would start down here with 1. You go 1, 2, 3, 4, 5, 6. Why? Because you would get, if you number it this way, you get 1 dimethyl, or sorry, actually it would be named differently, right? It would be 3-ethyl, because you put it in the alphabetical way. So it would be 3-ethyl, 1,1-dimethyl, cyclohexane, right? See that? And so the 1,1-dimethyl beats having 1-ethyl, 3,3-dimethyl, right? Does that make sense? So, but in this case here, we just discussed that one of the problems that it's really there, it's just a tie, so then you go by the alphabet. Okay? So I'll get you an apple. That was a good question. not that many apples. Can you catch it? It's pretty good. Okay, next one. This one. Who wants to try? Yeah. We go. Good. You can do the next one, okay? Yeah, start please by numbering the parent chain. Otherwise, by highlighting the parent chain. Okay. Okay, I think is that right? That's a secondary butyl substituent, right? I think it's right. So actually, here is a tricky part. I think, unless I'm mistaken, I think secondary butyl is really what you do is because the sec part, this one, is a prefix. And I think the prefix we ignore when alphabetizing. Remember? So actually that depends on now different. I know for tertiary butyl you ignore it. I think for secondary butyl, as far as I remember, you ignore it as well. But I think for isopropyl, then you might not ignore it. So for some you ignore it, for some you don't. And I think the rule I said in lecture is just ignore the prefix, right, for alphabetizing. So I think what we would really want to do, I think in an exam I would count this correct, because that's really a minor thing. But ideally, I think the name you would want to call it more correct, I think would be calling it 5-sec-butyl, and because the B comes for the E, right? And then 4-ethyl, 3-methyl nonane. Does anybody have the name with a, not with secondary butyl, but with a complex substituent? Nobody. Okay. So how about we make up another example? Let's do this. I want to make sure you know both ways. Let me make up. Okay. Here we go. Let's shrink this a bit. Okay. So that's this. Oops. Let's try again. Okay. Let's say we take another space here, and we make up one like this. Similar, but let's say we gonna go like this. Sorry. Now it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9, so then we're gonna give it this one a longer one. Okay, so it's still the main chain doesn't change. Okay, so now let's see. We can do this together. We'll have the main chain would still be the same. But now it's a decane, okay? So we would start numbering over here. 1, 2, 3, 4, 5, right? 6, 7, 8, 9, 10. Okay, so far so good, right? And so it would still be a 4-ethyl, 3-methyl decane, right? But now the question is, what's the name of this substituent? Right now it's more complex because it's not one of those substituents, those special ones you learned. So can you guys try to make up a name for this? Who wants to try? I just want to make sure you're comfortable doing this with complex substituents. You want to try? This is a hard one.
Would it be like 5-methyl butyl?
Let's see. Do you want to write it? It depends how you write it too, okay? So, but let's look at it. You have to look at the complex, at the substituent here, at this part, right? And you look at the parent chain of that substituent. So that's what I just highlighted. So that's a butyl. That's what you said. That's correct. Okay. But now, how do you number it? Yeah.
You just put the one right where the methyl is?
Yes, you put the one right where the methyl is, so over here.
Yeah.
But because the rule is where it starts to branch off the main chain. That's where you start numbering the side substituent. So it would be 1, 2, 3, 4, right?
Yeah.
So it would be, the substituent is called a 1-methyl butyl. Okay? And so now, that you alphabetize as M, as methyl. And the other one is just you have a methyl there. So let me see. So I guess methyl comes before 1-methyl butyl. Okay? So then we assemble the whole name. So it would be, let's see, we have enough space to write it. So the ethyl comes first, right, in the alphabet. So we say 4-ethyl. And then the methyl comes next, right? 3-methyl. And so now the important thing is you have to put the 1-methyl butyl all in parentheses. Otherwise it's not clear, okay? So then you have to say 1-methyl butyl. Then we're done. We call it decane. Decane. Congratulations. All right. Did I get something wrong?
So you added on the fifth carbon, so...
Oh, yeah, absolutely. You see, I got it wrong. We forgot to put the 5, right? It's because we need to say that this substituent is in position 5. In position 5, we have a 1-methyl butyl substituent, so we need to put that there before. Okay, sorry. You see, I make mistakes here too. Absolutely right. So this is I think the correct name. Yes?
Do you put a dash after the C before you say decane?
No.
Okay.
No, you don't. I just had to break the line, so I said
Yeah.
they can. But you don't put a dash. Yes?
How do you know that the methyl becomes before methyl butyl? Alphabetical?
So that's a good question. If you have, what comes first, Alex or Alexander? Alex. I think if it's longer, I think the shorter stuff comes first. I think that's the alphabetizing rule. I was just guessing, but I think it's the same, right? I think Alex would come before Alexander. That's what's going on. Yeah.
So what level do you ignore the prefixes again? So like if it was,
Ignore the prefixes for alphabetizing. Let's learn that as a rule.
so ignore the prefixes?
Yeah.
Then wouldn't the butyl be the first one again?
Right. No, but it's 1-methyl butyl.
So that changed.
So the methyl is not a prefix.
Okay.
The prefixes are like di, tri, tetra,
Okay.
tert, sec, those kind of things. If you have a 1-methyl butyl, then it's a methyl butyl. It's like a word. You ignore the 1, but then you start methyl butyl. The methyl is not a prefix. It's like a substituent. The dimethyl, the di would be a prefix. Okay, good question. But just so for now, let's say we ignore the prefixes for alphabetizing. So secondary butyl is just the same as butyl. Tertiary butyl is just as butyl again. Okay, it doesn't go with T. It goes with B. All right, pretty good. That was a good example. You learned something. We go to the next one. This is a hard one because I didn't actually teach you how to do it. Who wants another apple? You want to try this one? Try this one. So what's the rule for bicyclic compounds? I was just working on a video to upload this, and then we will learn. But the book talked about it. It's just, and we had one example in lecture. So switch to maybe the red one.
I forgot how to do that.
It's like the first one, yeah. So what we do with bicyclic compounds is we basically just say bicycle and then the total number of carbons in the framework. And then we have to analyze the bridges, like how many bridging points there are. Okay, so bicycloundecane, that's great. And now, yes. No, almost. You got close, but it's a little different. But you got, so the bicycloundecane is correct. Okay? So now the question is, how do we denominate which type of bicycloundecane it is? There's different ways to do this. But there's many different bicycloundecanes. So what you do is do the following. You look at, you see these 2 points. These are the so-called bridge heads. Okay, which holds everything together. You guys see that? Those are the special points. So those are the ones you ignore. And now you look, if it's a bicyclic compound, each bridgehead should link together 3 parts. Okay, it's kind of like a wireframe, right? And so let me show you what those 3 parts are. One is this part here, right, the green part. The other thing is this, let me change to another color, like red. Okay, so the other thing is this thing. That's the other linkage, right? And you have a third linkage, which we're going to do in blue, which is up here. Okay? You guys see these 3 linkages? Now what we need to do is tell how many carbons are in each linkage. Then we're done. And this is special notation for it. So the blue linkage, how many carbons there are? 2. Right? Here and here. 2 carbons, 2 CH2 groups. So this is we call it a 2-carbon bridge. Okay? Now, over here, how many carbons? 3. Right? So this is a 3-carbon bridge. And in the red part, how many carbons? 4. Right? And so what we do now, bridge. So what we do now is before the bicycloundecane, we just say what bridges we have. And we do this with these brackets. Okay? That's just special notation for these bicyclic compounds. And so you order them in, yeah, you start to order them with the largest bridge first, and then you go to you decrease the numbers. So you say 4 is the largest bridge, right? Then you put a dot instead of a comma. 4, 3, 2. That's what it is. It's a 4-3-2 bicycloundecane. Okay? So, what we need to do is practice this stuff, okay? So I'll upload a video which talks about all these rules, and then we'll do a couple examples in lecture, okay? Probably on Friday or on Monday next week. Does that sound good? Because I realized we actually didn't really talk about it in lecture, but so you used to get a preview on how to do it. Okay? The book talks about it. I think that's how to do it. What you do not need to know for the exam is how to number these bicyclic compounds. You see where it gets really complicated is if we then do this. You know what I mean? If I give you substituents, then you need to know how to number the bicyclic framework. And to be really honest with you, I have no idea how to number it myself. Like, you can learn it, but it's not, you don't need to know it, okay? I want you to be able to name the simple bicyclic frameworks. You just find the bridgeheads and you number it, okay? But that's the extent of what you need to be able to do. What happened? I deleted this thing. Okay, let's go to the next one. Okay, which of these are constitutional isomers? Yeah, we'll get to you. Switch again to maybe red. Right? So see. I hadn't thought about this myself. Did everybody get an apple? 1, 2, 4. Okay, let me give you an apple. Let's see, does anybody have a different number, a different answer? Just speak up. Let's see. Yeah.
I just 1 and 4.
You had 1 and 4. So you think 2, okay, 2 has a different number of hydrogens? That's right. Actually, that's right. You see, I didn't see myself. So, oh, okay. So yeah, you see, whenever you make a ring, you lose 2 hydrogens. Okay? Remember? So they can't have the same number of carbons and one has a ring or a double bond or a triple bond. They actually can't have the same number of hydrogens. So we'll take the 2 off, right? And 3 doesn't have the same number. Okay, so then it's fine. So this is then still a fairly easy problem because you just have to count the number of carbons. Okay? The difficult part, what you have to be able to do, is this. Let's say I give you, let me do another example here. I give you something like this. Versus this. So these constitutional isomers. No, they're the same, right? These are the same. So you see what I'm saying is what's hard is if I'm mean, I will draw the same compound just looking very differently. Like there was one of these examples on the exam, with this stuff which had a bunch of oxygens. And one I drew more in a circle-like structure, and then I just stretched it out, but it was exactly the same thing. Right? And a lot of students thought they were constitutional isomers because they look very different. So I want you to be aware that if things look very different, doesn't necessarily mean they are not the same thing. They can just be drawn in different ways. Right? And so these are the same. I would say identical. The other thing, of course, is that now we have learned different things like Newman projections. We can draw chair conformations of cyclohexane structures. We could draw things with wedges, with dashes, or with different ways to represent molecules. And if I'm really mean, I could give you, for instance, a Newman projection of a cyclohexane and then a line wedge drawing, a line drawing with wedges and dashes, and ask you, is it the same or are they constitutional isomers? And then in chapter 5, next Friday or on Monday, we'll certainly get into chapter 5. We'll talk about stereoisomers. And it's not just are they connected the same way, but also are they pointing in the same directions in space, right? And you can rotate molecules around, and then see that's where it gets really complicated. And again, what will help you is to get the molecular models, okay? Because what's cool about the molecular models is whenever you can rotate them around a bond. Like in a real molecule, like you can rotate around a single bond, you see that in the Newman projections. You can also do that with your models. So you can actually take your model and bend it into a different shape, and you will see that it can make both shapes. That will help you with these sorts of questions as well. Okay, it's really, so get those models. I recommend it. Any questions? Yes?
How do you name compound number 2 there?
How would you name the lower one? This one?
No, the one from the question.
Oh, then the one from the question. Okay, you bring me to another point, actually. One way to see whether they are the same or not, one easy trick is you name them both. If they have the same name, they're the same thing. Okay? As long as you're really good with naming, just name them. And even if it's drawn differently, right, the parent chain, you'll see it's the same, and then that's another helpful trick. So the one, which one were you wondering to name? Oh, number 2, like this one. Ooh, this one.
Yeah.
What's the name of this one? That's a good question. 1, 2, 3, 4, 5, 6, 7. So yeah, ooh. Okay, let's do it. Let's try. Which one is the parent chain? You could either pick the cyclohexane, That's an option, but remember the side chain here is kind of longer, isn't it? 1, 2, 3, 4, 5, 6. Okay, yeah, you have 6 carbons in each. So the easiest thing to do is to pick the cyclohexane as the parent, right? This one. And so now first thing we have to figure out is how to number the cyclohexane, right? So you want to do the numbering in a way so that the substituents get the lowest possible numbers, right? And so you can start. So one possibility is to do this: 1, 2, 3, 4, 5, right? 6. Or you would get 1, 2, 3, 5 in this way. The other way you can do it is 1, 2, 3, 4, 5. Okay? And so they're the same. Right? So there is a tie. That means we now have to go by the alphabet. So it doesn't matter. You see, it will give you the same. Because it's 1, 2, 3 trimethyl, and then the 5 is the other substituent. So it doesn't matter which way we number it, as long as you start with one of the methyls. Okay? So we'll go like this, 5, 6. Okay? And now, so it's basically a 1, 2, 3 trimethyl cyclohexane. Okay? And now the only thing we have to figure out is how to name, again, this complex substituent, which is not one we have learned. So to name it, remember the rule is you find the parent chain in that substituent, and so that will make that green. Again, that's the longest chain of the substituent, this one. Okay? So, and then you number it, again, starting from where it's attached to the parent chain. So 1, 2, 3, 4, 5. So you see, it's a pentane, a pentyl substituent. And then in position 1, you have a methyl. And in position 3, you have a methyl. You guys see that? And so now we have to just assemble it. So the side chain substituent is a dimethyl pentyl. Right? So that starts with M. So methyl pentyl. And the other substituents here are just methyl. So which one goes first in the alphabet? The methyl, because you ignore the di of the dimethyl pentyl, right? And again, it's shorter. The methyl is short, like Alex versus Alexander, right? Alex comes first. So these guys come first. The methyl the methyl ones come first. So let's just write it down. Okay, so you have to say 1, 2, 3. Trimethyl. Oops, sorry. Let's see. Trimethyl. And now we need to put the complex substituent, which is in position 5. I think you don't put a dash here. No, I think we do. 5. And now we rename these two guys. Right? 1, 3 dimethyl pentyl and cyclohexane. Does that make sense? So that's this guy. Questions? Yeah.
So that pentane is not a hexane because you like start counting the parent chain from that first carbon that's attached to it.
Yes, it's not a hexane because you have to start counting the parent chain from where it leaves, where it comes off the main chain. The main parent chain. You can't have, yeah, I know what you mean. What you would like to do is just simplify the naming. You would like to do something like this. Right? You can't. Because position 1 always has to be the one which is attached to the main parent chain. Okay? Any other questions? This is a good question. Yes, please.
The pentyl, it has to be YL instead of AIM because it's like this. That's a part of it, not all.
Because it's a substituent. Yeah, you don't say 1,3-dimethyl pentane cyclohexane. Because it's the pentyl, it's a substituent, you always end up with YL. It's just a really complex substituent. Okay? So that was a very helpful example, I think. Thanks for the question. I'll get you an apple. We're running low on apples, but that's fine. So you see, the real question was fairly easy, but the naming of this was hard. So what you have to do with naming is you can pretty much make up problems too. There is software out there which can name compounds. I don't know, has anybody of you used Chem before? Called CHEM and then DRAW. So we have a license. What you can do is you can download it. I think it can name compounds. ChemDraw. Although I have to probably take back my word because the license we have doesn't allow you to do the naming. Because we have a basic version. Like I use an illegal version, which is more it's more powerful. It's an older one. But yeah, go ahead.
If the pentyl chain had like 2 more carbons and was longer than the hexane, the cyclohexane, would you then name the cyclohexane
As a substituent?
Yes.
Yes.
Would
Yes.
you call it hexyl?
Yes.
Okay.
So yeah, you're absolutely right. So if we had 2 more carbons on the pentane, something like this, then this would be a heptane, right? So then the main parent chain would become that heptane chain, and then you would name the cyclohexane as a cyclohexyl substituent.
Okay.
Absolutely right. So that makes it then even more complicated to name. What I will do for the naming, okay? Like obviously you see, for the naming stuff, it can get infinitely complex, okay? And it can get infinitely difficult for me to grade, right? Particularly if I want to give you partial credit. So I will try to stay with, I will not give you the easiest examples only, but I will also try to stay away from giving you the hardest possible thing I ever can come up with, okay? Like it's just as long as you, as long as you can do the book problems, the level of the book problems in terms of naming, that's kind of the level you need to know for the exam, okay? Plus the other thing which will be on the exam is, we will name stereo compounds with stereochemistry. We'll learn that in chapter 5. So that will be a part of the name. So that you have to know as well, okay? This is a different thing. This is about combustion equations. I just want to make sure you can balance them. You guys want to do it? Or you have a question? You want to try? Let me give it a try. So see if you can balance it and explain a little bit how do we do it. We first balance, because you guys did this in Chem, right? Balancing equations. There's some tricks I just want to make sure you can do it. Because this is helpful. You can balance the combustion equations. You can figure out how much energy is released in the reaction, and I will show you in a video how this gives some sort of.
Well, I don't know. So you just count the carbons. 5 times 2 is 10. And then you put 10 over there. So then there's 20 oxygen there, and then you have to count how many hydrogen there are. So like each one's 2.
Yeah.
1, 2, 3, 4, 5, 6, 7,
So
8,
10
9, 10.
hydrogens, right?
Yeah. 20, and then they're squared. So then that's
Oh, because there's
30.
Yeah.
So then that's 30, and then
Let's see. Okay. So the final answer, let's see. Thank you. So the final answer is, so it's 30 oxygens, right? Because we have
yeah, those are just like the
30 oxygen. Yeah. Perfect. So I'll just leave the final answer here for people to. Did anybody have anything else? That's fine. Just make sure you're able to balance these equations, right? Balance the carbons first based on how many carbons you have on the left side. You figure out how many CO2s you have. Then you balance the hydrogens, and then the oxygens, right? Okay, so. Okay, now we get to some different stuff like Newman projections. You want to try? Okay. These are typical exam questions for like the second exam. They're like, you can either write Me for methyl or CH3 for methyl. Right, that's fine.
I'll just put both.
Okay. Good. Perfect. Good. Do you guys have any questions? I think I have the last apple.
Oh, it's already happened.
Oh, you already have one? Okay. You can save one. Do you guys have any questions? Yes, please.
So does a wedge always indicate that the atom is on the left?
So the question is, does a wedge always indicate whether an atom is on the left? You mean like the wedge, for example, the wedge here with the chlorine, right?
Yeah.
No, it depends how you look at it. So let me show you. If we looked at the same compound, I'll do that down here, okay? If we look at the same compound, I'll do it in a different color so it doesn't confuse people. If we look at the same compound from the other direction, then it will be actually on the right. So let me show you. So if we do this, exact same compound, but now we look at it along this direction. Okay? We look at it along the other direction. Now how does it look? Now in the front, now the bromine will be, oops, let's see, here we go. The bromine will be on the left, and the methyl will be on top. By the way, it's better to draw CH3, but you could also leave it out. You just leave it as a corner there. And now the chlorine, you see the methyl is down, but now the chlorine is on the right, and the hydrogen is on the left. Guys, see that? So now it's completely different. Does that answer your question?
Yeah.
So the answer is no. It depends on how you look at it.
Okay.
It's really a matter of how you look at it.
I've been struggling with this.
So yeah, this is hard. This stuff is hard. Like when I look at these new, I have to think pretty carefully so I don't get it wrong. Okay? Like this is not an easy thing to do. You have to practice this. You have to pretty much just sit there and try to imagine it. That's the best way to do it. Or get your model out, build it, and then do it with the model. You do the first couple problems with the model, and then try to leave the problem, get rid of the problem. With the modeling kit. Then you leave the modeling kit away for the future problems, and see if you can do it without it. You know, to try to imagine it in your. It's really three-dimensional, imagining the thing in 3 dimensions. By imagining, basically what you have to imagine is you come here and you look at this molecule from this side, right? And it certainly helps very much to draw in the other substituents, right? If you put in the H here, and if you draw those, that helps, right? Because you can look at it like this, and you see, all right, this is pointing down, this is coming out of the board, this is going in the board, so this is on the left side. But if you look at it like this, it turns around. Make sense? Yes?
Does it matter so say like you wrote that the chlorine and the hydrogen were like on the like switch, would that still be right?
So you mean, oh, I see. So if you're saying if you wrote it with these two guys switched like this, then it will be wrong. And we will see in chapter 5 why. Because actually what you have here is a stereo center. So if you flip them, you will get a different compound, a different stereoisomer of the thing, if you are unlucky. And then, so yeah, it matters. Every little detail for these things matters. It's really hard thing to do, actually. That's why I put a couple of these Newman projections on the problem. Yes?
So then, I guess would the takeaway be that it's more important that the chlorine and the bromine are on opposite sides of each other than on...
Which side?
That they're like opposite of each other rather than which side you put either one on individually?
So yeah, that's a very good question. The question is, does it just matter where the bromine and chlorine are on opposite sides, or also on which side they are actually on? Actually, everything matters.
Yeah.
So one thing we're going to look at, this has something to do with diastereoisomers versus enantiomers, which we're going to talk about in chapter 5. If you flip the chlorine and the bromine both, you will get, in this case, you would get enantiomers. So they will be mirror images of each other. And then mirror images of they're called enantiomers, and we'll talk about that. Okay, but so as soon as we are through chapter 5, the problem is the exam will include chapter 5, because we'll get through chapter 5 by the time, exam number 2 comes along. And so you will pretty much have to do it right. The best way for these Newman projections, you really look at it and just draw it exactly as it's drawn. Okay? Just thinking about looking at it from the side. Make sense? So yeah, everything matters. in this case. Sometimes it doesn't, but almost always it matters. All right, let's go to the next one, right? Let's see. We have a couple more examples here. Who wants to try that one? Give it a try. They're all similar. So once you figure out how it works, then it becomes easier. They're all sticking out.
Oh, that was really ugly.
The only thing I've left is an orange.
She has an apple.
Oh, you have an apple.
Mm-hmm.
Don't look too sad. It will be fine. You just have to practice. It's fine. If you really know well how to do this, it will buy you a lot of points on the exam. It's like not just the Newman projections. As soon as you figure out how it works, it helps you with other things as well. Okay? Like a really
Oh no.
sounds worse. This is a typical placebo. All right. Is this good? Let me take a look at it. So the front side is good, and the back side.
Shouldn't there be a methyl group instead of the hydrogen?
Exactly.
Yeah,
Yeah.
that should be a CH3. I have it in my
Mm-hmm. The one in the back, right? This should be a CH3. Right? Okay? That's fine. Okay. Next one. You want to try? Try it. It's very easy, to make these mistakes, even if you have it in your note. So what I'm saying is, but this happens to people a lot, right? You do, for example, you do it correct on your scratch paper, and then you transfer it, and you forget to write a method. And then it's wrong on the exam. So you have to be absolutely, double check yourself like multiple times in different ways on the exam. Even just transferring things from the scratch paper to your exam in the end. Okay? Let's see. Trying to look at it. Okay, thank you. So we have ethyl. Okay, I see. So yeah, I'll help a little bit. So this is the front carbon, right? And the ethyl is pointing up. Generally, people capitalize it. Okay, that's fine. It's just, I think that's what people generally do. Ethyl, and then methyl is down to the right. Right, that's this orange piece here. And the hydrogen back here is down to the, sorry, the methyl is down to the left and hydrogen is down to the right. Then the ethyl in the back, in green here, is pointing down. The methyl, this one, is pointing up and to the right. And finally the hydrogen here is pointing up and to the left. Okay? Very good. Next one. Any questions? Yes?
Could you write out C2H5 for apple? Or do you want
Oh, good question. Could you write out C2H5? Absolutely. The other thing you can do, let me show you, is this. Like, you don't have to necessarily abbreviate everything. You can just leave it as it is. So you could do this. You could draw the wheel. And you can be, okay. So here we have an ethyl. Right? Here we have a methyl. Here we have an H. You just have to draw the H so it's clear where it shows up. Right? And then here's another ethyl. Methyl. H. So this is also fine. You see, or you could write C2H5 instead of ET. That's also fine. All of these things are perfectly fine. Yes? CH2, CH3 is also fine. Yeah. So we're talking about different ways, like either you kind of as a molecular formula for the substituent or a, abbreviation of the name, right? Or just line drawing or condensed or partially condensed structures. That's all fine. In the literature, you see literally a mixture of everything, whatever is most convenient. Okay, good. So next one. Okay, now we go to reverse. Right now we need to take the Newman projection and draw a wedge line drawing with everything. It's the same problem, just reverse. Who wants to try it? Good. Thank you.
Do you want the orange? Or?
Oh, I'm good. Thank you.
I will eat the orange.
Okay, good. Good, I think it's good. So which way are you looking onto the Newman projection?
So from here.
So like kind of like from here?
Yeah, so you look down this way. So this would be the front.
Yeah. Yeah, you look at it, you can look at it like this, you can look at it like this. You see, you can draw it in different ways, right? There's many correct ways to do this problem. I think your answer is fine.
Okay.
Right? Any questions? Yeah.
This way is this right, or is this?
Can you draw your answer? Let's draw it on the iPad. Let's see what people think. Right, let me just take off the, I think this is the way we look at she looked at the structure. Just take it off so you can draw yours. What do you guys think? Same thing or not? It's the same thing. It's the same thing. Same thing. So when you look at the only thing I don't like is the way you drew the arrow we are looking at. We would look at it like this. Right? You always point the arrow the way you're looking at it, point it parallel to the bond you're looking at. Yeah?
Do you need to draw the hydrogens?
No.
Okay.
So actually,
Like if I just did the dashed.
maybe you can You can draw yours.
It's like
Try.
the same thing as that, but
Yeah.
without it just like that.
Let me see again.
Can you just assume that the hydrogens
That's fine.
are?
Yeah. That's actually fine in this case. Yeah. So you can do it like this. Right?
Yeah, but except I did mine dashed.
Okay, let's see.
Because I was looking at it like.
So maybe mine is wrong. So you can't just
looking
flip
at
them
it
here.
like- I'm looking
If
at
you
it-
flip them if you flip them the wrong way, then they get wrong. That's the problem. So maybe let's draw yours
It's the
and
same
then.
one as what she just drew. Except,
Oh, okay.
Except there's no hydrogen wedges. It's just the dashed.
Yeah. The thing is, if you flip them, like if you flip the H and the Br, obviously the bromines are always on the same side. But if you flip the hydrogen and the bromine, then it's wrong. So I'm just trying to double check.
Looking at it from that way for it to be the.
So yeah, the first one is absolutely correct, I'm sure, because you can see kind of how it looks. Now the other one is kind of rotated. You're looking at it from the back side here. No, I'll show you. I am pretty sure, actually. I think I'll take my word back. I think this one, is the mirror image of this one.
Yeah, it is.
It is, right? They are mirror images.
Yeah, I'm looking at it like directly, like.
No, they're not. No, they're not. They're the same. Okay. They're not the same. They're the same. Okay, they're the same. They're not mirror images.
Yeah, that's it.
They're the same. If you flipped these guys, then it would be the mirror image.
Yeah.
So it's not the mirror image, so it's fine. Okay? So they're the same, and in this case mine here, but these two would be mirror images. See, so mine is incorrect. Okay? Yours is correct. So if you drew it like this, that's what you have, right?
Yep.
That's correct. Okay? Sorry, but you see what I mean? You have to be very careful about whether you're drawing the mirror image or not. It's gonna throw you off. It's very easy to mess up things. All right, next one. One more question. Oh, you want to do the last one? Okay, good. Does anybody else want to do the next one? Okay, we'll have you do it. Thank you. Is this the last one? This is the last one? Perfect. That's good. If you dash it, they get very big.
Yeah. Sorry.
It's okay. Thank you. That's great. Does anybody have another solution with just drawn in a different way, or that's fine? Okay, if not, I think we're pretty much done for today. We will keep, you guys can keep studying, okay? See, the problem is the material is getting harder now, right? Or, you know,